This is an example of vector addition where you can solve a problem involving accelerations where the two acceleration vectors are measured relative to each other. Um, in this case, a man is experiencing simultaneous forces that would actually cause two different accelerations that act in different directions. I'm going to start off by picking a drawing scale. This drawing scale will enable me to make the vectors fairly large so that I can increase my accuracy and precision. Now, the first vector is described as 3.5 feet per second forward, which forward really could mean just about anything. You could draw that to the right on your paper, you could draw it up on your paper. It's fully up to you. The key thing, though, is that you draw the next acceleration in the right direction relative to the first one. So I'm going to start off by drawing my first vector up on the paper to represent forward. So I made the first vector 7 centimeters long according to my scale, and I pointed it up to indicate forward. Now what I'm going to do is make my second vector. My second vector needs to be measured relative to the first one. So what I need to do is I need to make a reference line that represents the direction of the first vector, like so. But I'm going to draw the second vector coming from this point right here, coming from the tip of the first vector. And since the angle is going to be measured relative to that, I need to bring my protractor up and rotate it in a way to where I can measure 16 degrees left of the first vector. That will be something like this, somewhere around there. If I take my ruler then and put it on that line, I can measure the length of that vector, and this is going to be about 9.8 centimeters long, which clearly is going to go into my text. And you know what? That's fine. That happens sometimes. I want you to see that it's important that you predict where you're going to draw things, and sometimes you need to adjust where you're going to draw them appropriately. So now I can see what the net acceleration that this man is going to experience. That net acceleration is going to be the dashed line that goes from the beginning of the first vector to the end of the last vector, like so. I'm going to move this label out of the way so that we can just focus on that red line. This red line represents the total acceleration that you will experience because of these two individual accelerations that happen at the same time. In order to be able to find that answer, I need to be able to bring my ruler and adjust it over here so that I can measure the length of that. Now, you can see that this ruler is too short. I have the advantage of being able to lengthen the ruler by spreading it out like this. You would probably have to use some other kind of technique to make this happen. When I look very carefully, it looks like my resultant vector is about 16.7 or 16.8 centimeters long. I'll say it's 16.75 centimeters long. According to my scale, that will be about 8.4 feet per second. So 8.4 feet per second is the magnitude of the resultant acceleration. The last thing I need to do is I need to measure the angle that the resultant acceleration makes with the original vector that I drew it in reference to. This angle appears to be about 9 or 10 degrees, so I will report it as 10 degrees left of the original vector. So that makes my answer 8.4 feet per second, 10 degrees left of the original vector.